Elements of group 13. The group 13 of the periodic table consists of elements boron, aluminum, gallium, indium, and thallium. Except boron, which is classified as a known metal, all other elements of this group are metals. Aluminum is the most abundant of these elements. It is the third most abundant element by weight in the earth crust. Boron occurs rather sparsely. Gallium is twice as abundant as boron, but indium and thallium are much less common. General characteristics of group 13 elements. Atomic and ionic radii. The atomic and ionic radii of group 13 elements are smaller as compared to corresponding elements of group 2. This is due to the increase in nuclear charge when we move from element of group 2 to group 13 in the same period. As we move from left to right in the period, the magnitude of nuclear charge increases, but the electrons were added on the same shell. Since the electrons in the same shell don't screen each other, therefore the electron experience the nuclear charge. In other words, effective nuclear charge increases and thus size decreases. Therefore, the elements of this group have smaller size than the corresponding elements of the second group. On moving down the group, both atomic and ionic radii are expected to be increases due to the addition of new shells. However, the observed atomic radii of aluminium is slightly more than that of gallium. While going from aluminium to gallium, there are also 10 elements of the first transition series of d block elements from which have electrons in the inner d orbitals. The d orbitals don't screen the nucleus effectively because of their shape and poor penetration power. As a result, the effectively because of their shapes and poor penetration power. As a result, the effective nuclear charge in gallium becomes more than in aluminum and in its atomic radius therefore decreases slightly. Second is melting and boiling point. The melting points and boiling point decreases on moving down the group. However, the decrease in melting points is not as regular as in boiling points. Third is ionization energies. The first ionization energy of group 13 elements are less than the corresponding members of the alkaline earth. This is because the first electron in the case of group 13 elements is to be removed from p orbital, while in case of elements of group 2, the electron has to be removed from s orbital. Since p orbital were at slightly higher than the s orbital, the electron in the atoms of group 13 is weakly held by the nucleus and therefore the first ionization energy is less. However, second and third ionization energies are quite high. When one electron is removed from outermost p subshell, the resulting ion has completely filled s orbital, therefore it becomes difficult to remove the second electron. The decrease in ionization energy on moving down the group is due to the increase in atomic size and screening effect, which is more than to compensate the effect of increase in nuclear charge. Consequently, the electron become less and less tightly held by the nucleus as we move down to the group. Hence, ionization energy decreases down the group. The sharp decrease in ionization energy from boron to aluminum is due to the increase in size. In case of gallium, there are 10 d electrons in its inner electronic configuration. Since the d electrons shield the nuclear charge less effectively than the s and p electrons, the outer shell electron is held fairly strong by the nucleus. As a result, the ionization energy increases slightly in spite of the increase in atomic size as we move from aluminum to gallium. The similar increase is also observed from indium to thallium, which is due to the presence of 14f electrons in the inner electrons configuration of thallium, which has very poor shielding effect. Fourth is oxidation state. The atoms of these elements have 3 valence electrons, 2 in s subshell and 1 in the p subshell. Therefore, all the elements can show maximum positive 3 oxidation state. Boron show consistently positive 3 oxidation state in its compounds. Except boron, the other elements also show positive 1 oxidation state. The positive 1 oxidation state becomes more stable as we move down the group from boron to thallium. In case of last element, thallium, positive 1 oxidation state has been found to be more stable than positive 3 oxidation state. Gallium, the third element of the group, appears to show positive 2 oxidation state in some of its compounds such as gallium chloride. The cause of stability of lower oxidation state as we go down the group can be explained on the basis of invert pair effect. The element of group 13 have 3 electrons in their valence shell and therefore exhibits oxidation state of positive 3. However, it has been observed that in addition to positive 3 oxidation state, they can also exhibit oxidation state of plus 1. The plus 1 oxidation state become more and more stable as we go down the group from boron, aluminum, gallium, indium and thallium. The positive 1 oxidation state of thallium is more stable than positive 3 oxidation state. For example, thallus compounds such as TLOH and TLClO4 are more stable than their thallic compounds. This is attributed to the inert pair effect. In the case of last element, after the removal of one electron from p orbital, the remaining electron behave like stable noble gas, don't take part in the compound formation. The reluctance of the s electron pair to take part in chemical combination is called inert pair effect. This helps to explain the stability of lower oxidation state for the heavier elements of a group. Fifth is electropositive or metallic character. Due to the high energy energy of the elements of group 13 are less electropositive as compared to elements of group 2 on moving down the group. The electropositive metallic character increases because the ionization energy decreases. For example, boron is a non-metal while the other elements of the group are typically metals. Sixth is tendency to form covalent compounds. The trivalent boron ion B3 positive is exceedingly small, therefore it would have greater polarizing effect on the neighboring anions. As a result, it would tend to pull off electrons from neighboring anions and thereby show covalent character. Thus, while boron generally show covalent character, the other elements exhibit ionic character also in its compounds. The elements of the group 14. The group 14 of the periodic table contains 5 elements: carbon, silicon, germanium, tin and lead. This group is known as the carbon family. General characteristics of the group 14 elements. First is atomic radii. The atomic radii of group 14 elements are less than the corresponding elements of group 13. However, the atomic radii increase down the family. The decrease in atomic radii is due to the increase in effective nuclear charge on going from group 13 element to group 14 element within the same period. As a result, the outermost electrons are attracted more strongly towards the nucleus and therefore atomic radius decreases within the group. The atomic radii increase on going down the group due to the increase in the number of electron shells. Second is ionization energies. The first ionization energy of these elements are higher than the corresponding numbers of members of group 13 elements. The first ionization energy are due to the higher nuclear charge and smaller size of atoms of group 14 elements. While moving down the group, the ionization energy decreases. This is due to the increase in atomic size and screening effect, which overweigh the effect of the increase in nuclear charge. Therefore, the outermost electron become less and less tightly held by the nucleus and ionization energy decreases. Third is melting and boiling points. The atoms of this group form covalent bonds with each other and therefore they are strongly binding forces between their atoms in both solid and liquid states. Consequently, the melting and boiling points of group 14 elements are much higher in comparison to group 13 elements. On moving down the group, the melting and boiling point decreases. Fourth is oxidation state and valency. The elements of group 14 show tetravalency by sharing 4 of its valence electrons. Therefore, they have oxidation state of +4. In addition, germanium, lead also show positive to oxidation state. It has been observed that on going down the group, positive to oxidation state becomes more stable. For example, for lead compounds, positive to oxidation state is become more predominant. This is due to the inability of s electrons of the valence shell of tin and lead to participate in bonding. In other words, the pair of electrons 6s in lead behaves as inert. This is known as inert pair effect. Fifth is metallic character. Due to the large ionization energy, the elements of this group are less metallic than the elements of group 13. Or moving down the group, the metallic character increases from carbon to lead. For example, carbon is a typical non-metal. Silicon behaves as a non-metal, but in certain physical property, it behaves as a semi-metal. Germanium is a metal, while tin and lead are typically metals. Sixth is catenation. This is one of the remarkable property of carbon to form bonds with itself. This property of forming bonds with atoms of the same element is called catenation. Carbon shows maximum catenation in its group. On moving down the group 14, catenation tendency decreases. Because of catenation, carbon atoms can link with each other to form a large variety of compounds such as linear chains, branch chains, and rings of different sizes and lengths as shown ahead. Seventh is allotropy. All the elements of the carbon family with the exception of lead exhibit allotropy. Allotropy is the existence of an element in two or more forms which has different physical properties but have similar chemical properties. The elements of group 15. It contains 5 elements, namely nitrogen, phosphorus, arsenic, antimony, and bismuth. This group is called regarding as nitrogen family. The general characteristics of group 15 elements. First is atomic and ionic radii. The atomic and ionic radii of group 15 elements are smaller than its atomic radii of the corresponding group 14 elements. This is because of increased nuclear charge or going down the group. The atomic radii increases due to increasing number of shells. Second is melting and boiling point. Melting points except for antimony and bismuth, and boiling point increases on going down the group from nitrogen to bismuth, the melting points of antimony and bismuth are usually low. Third is ionization energy. The first ionization energy of the group 15 elements are higher than the corresponding members of group 14 elements. The larger ionization energy is due to the greater nuclear charge, smaller size, and stable configuration of the atoms of group 15 elements. The electronic configuration of atoms of group 15 are half filled and are stable, therefore they have high ionization energies. On going down the group, the ionization energy decreases. It is due to the increase in atomic size and screening effect and overweigh the effect of increased nuclear charge. Fourth is electronegativity. The electronegativity value of elements of group 15 are higher than the corresponding elements of group 14. The elements of group 15 have smaller size and greater nuclear charge of atoms, and therefore they have high electronegativity values. On going down the group, the electronegativity value decreases due to the increase in size of the atoms and shielding effect of inner electrons shells. On going down the group, fifth is oxidation states. These elements have 5 electrons in the valence shell. The loss of 5 electrons is quite difficult because of energy consideration, hence they don't form ionic compounds by loss of 5 electrons. On the other hand, these elements can also gain 3 electrons to complete their octets. By gain of 3 electrons is also not energetically favorable. However, they don't form ions by gaining 3 electrons from highly electropositive elements. Sixth is metallic character. The change from non-metallic to metallic character with increase in atomic number in the same group as shown by group 14 is also exhibited equally well by the elements of group. The elements of group 15 are less metallic. However, on going down the group path, the metallic character increases from nitrogen to bismuth. For example, N and P are non-metallic while As and Sb are partially non-metallic while bismuth is a metal. Seventh is catenation. All the elements of group 15 can show a tendency to form bonds with itself. It is known as catenation. All the elements show this property but to a much smaller extent than carbon. For example, hydrogen has 2 N atoms bonded together. Hydrazoic acid has 3 atoms. Azide has also 3 bonded N atoms, while diphosphine has 2 phosphorus atoms which bonded together. Eighth is allotropy. Except nitrogen, bismuth, all other elements of this group show allotropy. For example, phosphorus exists as white, black, or red phosphorus. Arsenic exists as yellow or grey arsenic. Antimony exists as yellow or silver-grey allotropic forms. Ninth is elemental state and chemical reactivity. Nitrogen is a colorless gas and exists as diatomic. The two nitrogen atoms are held together by triple bond and have very good bond dissociation energy. Due to the presence of triple bond which has very high bond dissociation energy, the nitrogen molecule has very low reactivity. However, the tendency to form multiple bonds p pi is limited only to nitrogen. On the other hand, phosphorus, arsenic, and antimony exist in various forms containing single bonded atoms. For example, phosphorus exists as tetrahedral P4 molecule are shown in figure. In this case, 4 P atoms lie at the corners of a regular tetrahedron. Each P is bonded to 3 P atoms by single P bond. Therefore, it exists as solid. Therefore, nitrogen exists as gas while phosphorus exists as solid. The elements of the group 16, the elements oxygen, sulfur, selenium, tellurium, and polonium constitute group 16 elements of the periodic table. They are named as oxygen family after the name of the first member of this group. The first 4 metals of this group are collectively known as chalcogens because many metals ores occur as oxides and sulfides. All these are non-metallic in character. The metallic character increases down the group. The last element of this family, polonium, has metallic character and it is a radioactive element with a very short period life. The general characteristics of elements of group 16. First is atomic and ionic radii. The atomic and ionic radii of the elements of this group increases on going down the group. This is due to the increase in the number of electron shells. Second is ionization energies. The ionization energy of the elements of oxygen family are less than the of nitrogen family. As we move down the group from oxygen to polonium, the ionization energy decreases. We expect that the ionization energy of oxygen should be more than that of N because of decrease in size. However, oxygen has an expectedly low ionization energy than N. This is due to the reason that nitrogen has completely half-filled orbitals and the configuration is stable because half-filled and completely filled configuration have extra stability, but the configuration of O is less stable and therefore has low ionization energy. As we move down a group, there is increase in nuclear charge, but this at the same time the atomic size as well as the number of inert electrons which shield the valence electron from the nucleus increase. The overall effect of increasing atomic size and the shielding effect is much more than the effect of increase in nuclear charge. Consequently, the outermost electron is less and less tightly held by the nucleus as we move down the group, and hence ionization energy decreases. Third is melting and boiling point. The melting and boiling points increases with increase in atomic number as we go down the group. When we move down the group, the molecular size increases. As a result, the magnitude of the van der Waals forces also increases with the increase in atomic number, and therefore melting point also increases. The melting point of polonium is however small. Fourth is electronegativity. Oxygen is the second most electronegative element, the first being fluorine. The electronegativity decreases on going down the group. This is due to increase in the size of the atoms. Fifth is metallic and non-metallic character. The first four elements, namely oxygen, sulfur, selenium, and tellurium, are known metals. The non-metallic character is stronger in O and S and weaker in Se and Te. On the other hand, last element is marked metallic, however, it is radioactive and is only short-lived. Sixth is electronic affinity. The elements of this family have higher electron affinities. The values increase down the group from sulfur to polonium. However, oxygen unexpectedly has low electron affinity. This is attributed to the small size of oxygen atom, so that its electron cloud is distributed over a small region of space, and therefore it repels the incoming electrons. Thus, the electron's affinity of oxygen is unexpectedly less in the family. Seventh is oxidation state. All the elements of this group have ns2np4 configuration in their outermost shell. Therefore, the atoms of these elements try to gain or share two electrons to achieve stable gas configuration. Since oxygen has a very high value of electronegativity, it tends to achieve the noble gas configuration, preferably by gaining electrons. Thus, oxygen exhibits oxidation state of -2 in its compounds. However, then a few exceptions in which the oxidation state of oxygen is not -2. For example, the oxidation state of oxygen in F2O is +2, while in S2O2 it is -1. Unlike oxygen, the other elements also show oxidation state of +2, +4, and +6 due to the promotion of electrons to vacant d orbitals. Eighth is catenation. Catenation is the tendency of an atom to form bonds with identical atoms. In this group only, sulfur has a strong tendency for catenation. Oxygen also shows this tendency to a limited extent. Therefore, the polyoxides and polysulfides of the following types are known. Ninth is elemental state. Oxygen exists at diatomic molecule under normal condition. Oxygen exists as a gas. In oxygen molecule, there is p pi overlap between two oxygen atoms forming double bond. The intermolecular forces in oxygen are weak van der Waals, and therefore oxygen exists as a gas. On the other hand, the other elements of family don't form stable p-pi bonds and don't exist as M2 molecules. On the other hand, the other atoms are linked by single bonds and form polyatomic complexes. For example, sulfur and selenium molecules have 8 atoms per molecule and have pucked ring structure. The pucked ring structure of sulfur is shown. Tenth is allotropy. All the elements of the group exhibit allotropy. For example, oxygen exists as O2 and O3. Sulfur exists in a number of allotropic forms such as rhombic, monocline, plastic, sulfur. All these allotropic forms of sulfur are non-metallic. Selenium have two common forms, red and grey. Similarly, tellurium and polonium occurs in allotropic forms. The elements of the group 17. Group 17 of the periodic table contains 5 elements: fluorine, chlorine, bromine, iodine, and astatine. These are named as halogen. The name halogen is derived from the Greek word meaning sea salt produces, because the first 3 elements occur as salt in seawater. These are non-metallic elements. The last member of the family, astatine, is a radioactive element. General characteristics of the group 14 elements. First is atomic and ionic radii. The halogens have the smallest atomic radii in their respective periods due to the maximum effect nuclear charge among themselves. The atomic and ionic radii increases with the increase in atomic number. This is due to increase in the number of electron shares. Second is ionization energies. The ionization energies of halogens are very high. This indicates that they have very little tendency to lose electron. However, on going down the group from fluorine to astatine, the ionization energy decreases due to the gradual increase in atomic size, which is maximum for iodine. Consequently, it has less ionization energy in family. Third is metallic and boiling points. The metallic and boiling points of halogen increases with increase in atomic number as we go down the group. The force existing between these molecules are weak van der Waals forces with increase down the group. This is also clear from the change of state from fluorine to iodine. At room temperature, fluorine and chlorine are gases, bromine is a liquid, while iodine and astatine are solid. Fourth is electron affinities. All these elements, all these have maximum electron affinities in their respective periods. This is due to the fact that the atoms of these elements have only one electron less than the stable noble configuration. Therefore, they have maximum tendency to accept an additional electron. In general, electron affinity decreases from top to bottom in a group. It is due to the fact that the effect of increase in atomic size is much more than the effect of increase in nuclear charge, and thus the additional electron feels less attractive by the large atom. Consequently, electron affinity decreases. Fluorine has unexpectedly less electron affinity than chlorine. Therefore, chlorine has the highest electron affinity in the group. The lower electron affinity of fluorine as compared to the chlorine is due to very small size of the fluorine atoms. As a result, there are strongly inter-electronic repulsion in the relatively small 2p subshell of fluorine, and thus the increased electron does not feel much attraction. Therefore, its electron affinity is small. Fifth is electronegativity. Halogens have high electronegativity values. The values decrease down the group from fluorine to iodine because the atom size increases and the effective nuclear charge decreases. Fluorine is the most electronegativity element in the periodic table. Sixth is metallic and or non-metallic character. Because of very high ionization energy values, all halogens are non-metallic in character. The non-metallic character decreases as we go down the group. Therefore, the last element, iodine, is a solid with a metallic luster and form positive ions. Seventh is color. All the halogens are colored. The color of different halogens are given below. As fluorine is light yellow, chlorine is greenish yellow, bromine is reddish brown, iodine is dark violet. Eighth is oxidation state. Halogens have only one electron is less than the next noble gas. Their oxidation state, halogens have only one electron less than the next noble gas. Therefore, they can get the noble gas configuration either by gaining one electron to form uninegative ion or by sharing electrons with other atoms. Thus, they show an oxidation state of -1 or +1. Since fluorine is most electronegativity elements, it is always shown as oxidation state of -1. It does not show any positive oxidation state. Ninth is chemical reactivity of halogens. The halogens are the most reactive elements of a family. Fluorine is the most reactive of all the halogens. The reactivity of halogens decreases down the group. The high reactivity of halogens is due to the following reasons. First is low dissociation energy, and the second is high electron affinity. Thank you.